Now let's solve some problems by using Parseval identity of Fourier series. How are we going to use Parseval identity of Fourier series to solve any problem? So the very first problem is problem number 1, where we want to find the Fourier series of x squared and then prove that 1 over 1 to the 4 plus 1 over 2 to the 4 plus 1 over 3 to the 4 plus so on equals to pi to the 4 over 90. We have two tasks to go for. The first one is to find the normal Fourier series of x squared, and then we're going to prove that this left side equals to the right side. Now we have done in introduction that we use the Parseval identity equation when we want to prove the expression with the constant identities which has powers more than 2. Remember, these are the constant identities. Let me just go back and reflect. That was our definition that Parseval's identity of Fourier series is used in a case where we need to prove an expression having constant identities with their maximum powers greater than 2. What are those constant identities and what are their maximum powers? Well, this is the expression where we have the constant identities with the power more than 2. Remember, it is 4. 4 is more than 2. 2 to the 4, 3 to the 4, pi to the 4. These are the constant identities with the powers more than 2. So if we have such situation where we want to prove such kind of expression, we need to take help from Parseval identity of Fourier series. We cannot use normal Fourier series because look, with the normal Fourier series we are only able to prove the expression with the constant identities with maximum powers of 2 less than 2 or equals to 2. We cannot use Fourier series for the powers more than 2. That's why we use Parseval identity of Fourier series, not a simple Fourier series. In such case, Parseval identity plays tremendous role. It can solve our problems. Otherwise, we won't be able to prove such expression. So first thing is first we're going to find the Fourier series of x squared. And then later in the second task, we want to prove that the left side equals to the right side by using Parseval's identity. To find the Fourier series of x squared, we need to check that whether the given function is even or odd. Look, we have done it in Fourier series. If you still don't remember what is Fourier series, how to solve the problems by using Fourier series, you're going to check the section of Fourier series. I have done many problems, how to solve them by using Fourier series. So before to go for the Fourier series, we want to check that whether the function is even or odd. Look, x squared is an even function. If you go through the process, what was the process? The process to check the even and odd function was we're going to multiply the x variable by negative. So negative x squared will be positive x squared. Therefore, it is even function. We know that for the even function, we don't have b sub n coefficient. B sub n coefficient is 0 for the even function. We have a sub naught and a sub n. A sub naught and a sub n are the only two coefficients that exist for the even function. B sub n is 0. So we are not talking about b sub n. We want to put simply b sub n equals to 0. What is the equation for a sub naught? The equation for a sub naught equals to 1 over 2 pi into integral of x squared dx. Look, we are talking about the full range, which is from 0 to pi. The formula for the a sub naught is 1 over 2 pi into integral of f of x dx. What is my f of x? My f of x is x squared. So I just plugged in x squared for f of x. Remember, this is the full range Fourier series, which is from negative pi up to positive pi. This is definite integral. So take the definite integral of x squared with respect to x. But before to go for the integration, we want to make the lower limit equals to 0 and the upper limit pi. And then we're going to multiply it by 2. Why? Because it is even function. So I can write 1 over 2 pi times 2 into integral of x squared dx. I made the lower limit equals to 0 and then multiplied it by 2. So 2 cancels with the 2. Now I'm going to take the definite integral of x squared with respect to x. So we'll have 1 over pi into x cubed over 3 with the limit from 0 to pi. Take the integration. Now apply the upper limit and then the lower limit. At the end you will get pi squared over 3. This is my a sub naught. Look, by applying the upper limit, x cubed will become pi cubed. So you will have pi cubed over 3 and then minus the lower limit. So x cubed will be 0 cubed. 0 cubed is 0, so 0 over 3 will be 0. For the lower limit, the function is 0. For the upper limit, you will have pi cubed over 3. Now, I have another pi here. So this pi will cancel with 1 pi here. I will left only with pi squared. Therefore, I have pi squared over 3. This is the value for coefficient a sub naught. Now I'm going to take the value for a sub n. The formula for the a sub n is 1 over pi into integral of x squared times cos nx dx. This is the typical formula for the coefficient a sub n. As we know that the function is even function, so for the even function we can make the lower limit equals to 0, and then we're going to multiply it by 2. So do the same thing as we did for a sub naught. Therefore I can write 1 over pi into 2 into integral of x squared cos nx dx. Remember, for the f of x we plugged in x squared because my f of x is x squared. Since it is even function, cos is also even function, so even times even will be even. Remember, you have to look to the cos and sine as well. So even times even is even. Therefore this whole function is even function. Therefore we can make the lower limit equals to 0, otherwise it is not possible. It is not possible for the odd function. You can only do this for the even function. So I will have 0 to the pi instead of negative pi to the pi. But then don't forget to multiply it by 2. Now since I have the product of two functions, x squared and cos nx, so I'm going to apply the product rule. There are two ways to find the definite integral of these functions, which is the product of two subfunctions, x squared and cos nx. But since it has one pure algebraic functions, therefore we can use one simple method where we have differentiation on one side and integration on another side. So we're going to take the derivative of x squared and we're going to take the integration of cos nx. We're going to repeat the process of integration and differentiation until on the left side for the differentiation we get 0. The moment we get 0, we're going to stop the process. If you are confused, just go and check the Fourier series section. I have done it. I have done that process. It's pretty simple. Now after finding the integration of x squared times cos nx with respect to x, I will have 2 over pi into x squared times sin nx over n plus 2x times cos nx over n squared minus 2 into sin nx over n cubed with limit values from 0 to pi. As I said, I'm going to take the derivative of the pure algebraic terms. You have to take the derivative of the pure algebraic term and integration of the other term. First put x squared as it is and take the integration of cos nx. Integration of cos nx is sin nx over n plus. Now to take the derivative of x squared. So derivative of x squared is 2x. And then the integration of this term. So integration of sin nx over n is cos nx over n squared. Because derivative of sin nx is cos nx over n, I have already n here, so n times n will be n squared. Repeat the same process. Take the derivative of 2x. So derivative of 2x is 2. And integration of cos nx over n cubed. We know that the integration of cos nx is negative sin nx over n. I have already n squared, so n squared times n will be n cubed. Now if you repeat the same process, you're gonna get 0 after this because derivative of 2 is 0, so 0 times anything will be 0. Therefore we're gonna stop the process here. Now to apply the values of upper and lower limits to have such expression, replace all the x variables by pi. X squared will be pi squared, this x becomes pi, this x pi, and also 2x is 2 pi. Wherever there is x variable, you're going to plug in x equals to pi. And then minus, apply the lower limit. For the lower limit, you're going to plug in x equals to 0. We know that according to the trigonometric rule, sin n pi equals to 0, sin n pi equals to 0. So these two terms become 0. And sine of 0 is 0. Sine of 0 is 0. Cos of 0 is 1. But remember that is 0. So 0 times 2 will be 0. And 0 times anything will be 0. For the lower limit, everything is 0. For the upper limit, I left only with the 2 pi into cos n pi over n squared. So I can write 2 over pi into 2 pi into cos n pi over n squared. Pi cancels with the pi, so I will left only with 4 over n squared into cos n pi. Look, there is a pi here, so this pi cancels with the pi. 2 times 2 will be 4. Take n squared out. So I will have 4 over n squared into cos n pi. We know that cos n pi equals to negative 1 to the n. So just put negative 1 to the n for cos n pi. Remember, if n is odd, the value for cos pi will be negative. If n is even, the value of cos pi will be positive. Like for cos pi, it is negative 1. For cos 2 pi, it is positive 1. For cos 3 pi, it is negative 1. For cos 4 pi, it is positive 1. Therefore, we put n here. It depends on the value of n. We know that actually cos pi is negative 1, but then don't forget there is n here. If it is odd, it will be negative. If it is even, it will be positive. So there I got the value for a sub n. Now I am going to plug in the value of a sub naught, which is pi squared over 3, and a sub n, which is 4 over n squared into negative 1 to the n. So the Parseval identity of Fourier series is this. Remember, we are talking about the Parseval identity. We are not talking about the simple Fourier series. So we're going to use the formula for the Parseval's identity of Fourier series. The equation for the Parseval identity of Fourier series is integral of f of x squared dx with the limits from negative pi up to positive pi equals to pi into 2 into a sub naught squared plus summation of a sub n squared plus b sub n squared. Look, we are taking full range from negative pi up to positive pi. We are not taking half range because look, our coefficient is in full range. So plug in the values of all the coefficients and the value of f of x to have integral of x squared to the whole squared dx, and for a sub naught put pi squared over 3. For a sub n put 4 over n squared into negative 1 to the n to the whole squared. For b sub n put 0. So 0 to the squared will be 0. Look, my f of x is x squared and my a sub naught is pi squared over 3. My a sub n is 4 over n squared into negative 1 to the n. What is my b sub n? My b sub n is 0 here because my function is even function. For the even function, your b sub n is automatically 0. Even if you do this process for the b sub n, you're gonna get 0 at the end. So we don't need to go through this process. Just simply put b sub n equals to 0. Therefore, my b sub n is 0. This is the value for a sub n, and this is the value for a sub naught. This is the value for f of x, which is x squared. Remember, there is a whole squared here. So square of 4 will be 16, and square of n squared will be n to the 4. But remember, if you take the square of negative 1 to the n, you will get positive 1. So you will have 2n. So for the 2n, you can make negative 1 to the squared to the n. If it is even, it becomes positive. If it is odd, it becomes negative. Since it is even, therefore, your negative 1 will become positive 1. So I will have 2 into integral of x to the 4 dx with the limit from 0 to pi equals to pi into 2 into pi to the 4 over 9 plus summation of 16 over n to the 4, with the n start from 1 up to positive infinity. As I said, negative 1 becomes positive. So 4 squared becomes 16. N squared becomes n to the 4. There is also a squared here. So pi squared is pi to the 4. 3 squared is 9. Here my function is even function, which is x squared. So I can make the lower limit equals to 0 and the upper limit pi. And then don't forget to multiply it by 2. Therefore, I have 2 into integral of x to the 4 dx with the limit from 0 to pi. Now take the definite integral for the left side. Integral of x to the 4 with respect to x is x to the 5 over 5 with the limit from 0 to pi. Put the upper and lower limit for the left side to have pi to the 5 over 5 minus 0, because for the lower limit it becomes 0. When I plug in x equals to 0, 0 to the 5 will be 0. So 0 over 5 will be 0. For the lower limit, the function is 0, and for the upper limit, x to the 5 becomes pi to the 5 over 5. Do further simplification to have 2 times pi to the 5 over 5 equals to pi into 2 times pi to the 4 over 9 plus 16 into summation of 1 over n to the 4. Just take 16 out of the summation. Since I have pi here, which is the product of this whole expression, can I cancel this pi with 1 pi here? Yes. I have pi to the 5. I have pi here, so this pi cancels with 1 pi, therefore I will left only with pi to the 4. It is a simple algebra. So I can write 2 times pi to the 4 over 5 equals to 2 times pi to the 4 over 9 plus 16 into a summation of 1 over n to the 4. Because this pi cancels with 1 pi, so from pi to the 5, I left with pi to the 4. Do further simplification to have 2 times pi to the 4 over 5 minus 2 times pi to the 4 over 9. Just bring this term to the left side to become negative. Take the LCMs of the left side first to have 18 pi to the 4 minus 10 pi to the 4 or 45. We are taking the LCM of the left sides. 18 pi to the 4 minus 10 pi to the 4 will be 8 pi to the 4. But what about 720? After taking cross multiplication, 16 will take multiplication with 45. So 45 times 16 is 720. Therefore, I have 720. So my expression is now h times pi to the 4 over 720 equals to summation of 1 over n to the 4. Now the further simplification. So I will have x to the 4 over 9 here. Therefore, I can write 1 over 1 to the 4 plus 1 over 2 to the 4 plus 1 over 3 to the 4 plus so on equals to pi to the 4 over 90. Because after simplification, I will get pi to the 4 over 90 here. Remember, it is the summation. It is the summation of 1 over n to the 4. So what is n? From 1 up to infinity. So I'm going to start from 1, plug in n equals to 1. Remember the power is 4. So I will have 1 over 4. And then n equals to 2. So I will have 1 over 2 to the 4. And then n equals to 3. So I will have 1 over 3 to the 4 and so on up to infinity. This is the infinite series. So there I got the proof that the left side equals to the right side. We just proved the expression with the constant identities which has powers more than 2. There I got the proof. This proof was only possible by using Parseval identity of Fourier series. If you apply the normal Fourier series equation, you won't be able to get such proof because the expression has the constant identities with the powers more than 2. Fourier series is only possible to prove the expression with the constant identities which has power equals to 2 or less than 2, not more than 2. When it comes to more than 2, you're going to get help from Parseval identity.